Last episode, the gradients did the opposite thing. They exploded, one layer spiking to 1000, and you reached for the clip to chop the spike down to 1. Clipping is a seatbelt, it catches the crash, but it doesn't stop the other failure, the quiet one. Stack a net deep enough and run the backward pass, and watch the gradient that reaches the first layer, 3.2 times 10 to the minus 7. Not a spike, a whisper. The first layers stop learning entirely. Tonight, the one-line idea that fixed it and let people train networks 1,000 layers deep. Here's the misconception that sounds obviously true. Deeper is strictly better, more layers, more capacity, lower loss. So you take a 20-layer net that works, you stack it to 56 layers, and the training loss goes up. Not the test loss, the training loss, the one a bigger model should crush. The 56-layer net is worse at the thing it has strictly more power to do. That's not overfitting. Something is broken in the optimization itself. The depth you added became depth you couldn't train. Why? Walk the gradient backward layer by layer. At each layer, the chain rule multiplies by that layer's local Jacobian. 10 layers means 10 factors multiplied together. If each factor is a bit less than 1, say 0.4, then 0.4 to the 10th is about 1/10,000th. And you keep going. By the input layer, you're at 3.2 times 10 to the minus 7. The gradient didn't get corrupted, it got attenuated, multiplied towards 0 by its own depth. The misconception is that signal decays down the stack. The truth is, it gets multiplied down, and multiplication by small numbers is merciless. So just make the local factors bigger, push them above 1. People try, now you're multiplying 10 numbers each above 1, and you're back in last episode's nightmare. The gradient explodes. Vanishing and exploding aren't two problems, they're the same problem, a product of 10 factors, and the only stable answer is for that product to sit near 1. Hitting exactly near 1 at every layer, every step, by tuning weights? You can't. The product is a knife edge, and the optimizer keeps knocking you off it. Now the idea. Instead of a layer computing y arcondon fx, transform the input into the output, make it compute y, fx plus x. Add the input back. The layer only has to learn the change, the residual, the difference between what came in and what should come out. If the best thing a layer can do is nothing, it just learns fx 0 and the input passes straight through. That's the misconception worth killing. A skip connection isn't extra capacity, it's the opposite. It makes do nothing the easy default, so depth can't hurt you. Watch what it does to the backward pass, because this is the whole episode. Differentiate y was under fx plus x. The derivative is f(x) plus 1. That plus 1 is a guaranteed path. A plus 1 term in the local factor no matter what f does. The gradient flowing back doesn't have to climb through the transform f. It can take the identity slide straight to the previous layer with its magnitude intact. Even when f shrinks to nearly 0, the exact thing that killed the plane net, the plus 1 keeps the door open. You can't multiply your way to 0 when there's a 1 in every factor. But surely adding the input pollutes the signal. You're mixing the raw input into a refined representation. That's the intuition that keeps people from trusting it, and it's backwards. The forward pass barely changes. F learns whatever small correction it needs on top of the identity. What changes is the gradient highway. Those pulse ones chain into a clean route from the loss all the way down to layer 1. In our toy, the plane net delivers 3.2 times 10 to the minus 7 to the first layer. The residual net delivers about 0.18 to the same layer, same depth. 6 orders of magnitude from 1 plus sign. One honest caveat so you don't overclaim. The skip needs fx and x to be the same shape to add them. When a layer changes the width, downsamples doubles the channels. You can't just add You project X through a small linear map first so the shapes line up, then add. That's the only real bookkeeping. The principle is untouched. Keep an identity is path open, and the gradient always has a way home. Open nn residual.py. We build two 10-layer stacks on the same input, the same weights, the same everything. The only difference is one path does h wound layer h and the other does h wound layer h plus h. We run one backward pass through each, grab the gradient norm at every layer, and print them side by side. The bars you'll see are those 20 real numbers. Top of the file, the toy block. Each layer is a linear map followed by a tand, deliberately initialized so the local Jacobian shrinks the signal. That's how we reproduce vanishing on purpose. Same blocks feed both stacks, so the comparison is fair. Nothing differs but the wiring. The plain forward pass, the loop everyone writes. Age, block age 10 times. Clean, readable, and quietly fatal. Each call multiplies one more shrinking factor into the eventual gradient. We stash each layer's input, so the backward pass can measure what arrives there. The residual forward pass, the same loop, one character different, h and block h plus h. The plus h is the identity shortcut. That's it. That is the entire architectural change that the rest of deep learning is built on top of. The backward pass and the measurement. We run autograd once per stack and read gradient, the L2 norm of the gradient, at each layer's input. For the plain stack, the norms march downward, halving and halving, until the first layer reads 3.2 times 10 to the minus 7. For the residual stack, they hold a flat band. The print block. We line the two columns up, layer 10 at the top down to layer 1, and tag the plain column's last entry as the vanishing floor and the residual columns as the survivor. The final summary line is the one the figure draws, plain first layer norm versus residual first layer norm. So that's the identity shortcut, not more power, just a clear road home for the gradient, +1 in every factor, so the product can't collapse. Next episode, the other half of the DeepNet survival kit. We added a path, now we normalize what flows down it, batch norm, and what it actually normalizes, which is not what its name suggests.